Hi everyone, I'm Steve. I used to joke that now that I use Windows, projectors just work, but projectors never work, no matter what you're doing. So this is a talk called Rust WebAssembly in the Future of Serverless. It's kind of like buzzword bingo a little bit, like who got bingo, all these terms in one talk. But we're gonna talk about how all these three things like fit together and where I see some of the stuff in this space going. I got the idea from this talk when I saw this tweet, because I saw this tweet and said this makes perfect sense, and then everyone else I showed it to said, what are you talking about? And so in some ways this talk is like an extended explanation of this tweet in some ways from my perspective. So this is Solomon Hykes, who co-founded Docker. We'll talk a little bit more about that later. But he says, if WASM and WASI existed in 2008, we wouldn't have needed to create Docker. That's how important it is. Like WebAssembly would replace Docker. And that was very confusing to a lot of people. And so that's sort of like the high-level topic of what we're going to talk about. But first, Rust. So Rust is a programming language, and we've iterated a lot on this slogan, and the latest version of this slogan is a programming language that's empowering everyone to build reliable and efficient software. You may have seen a previous slogan involving threading and memory safety and stuff, but that was even more buzzword bingo-y than the title of this talk. And this is like really gets to the guts of what Rust is about. Rust is a programming language that lets you build stuff that is as low or as high level as you want, and is incredibly fast and like resource efficient. A lot of people, and like the way that we've talked about Rust in the past, I'm on the Rust core team, by the way, I guess I didn't say that earlier, but the way that we talk about Rust in the past tended to be as a C++ replacement, because the intention, like the reason Rust got made in the first place was at Mozilla. So Firefox is a great piece of software, but has security vulnerabilities like any browser does. And it turns out that a significant number of them, like over half, were due to a thing called memory unsafety, which basically means you use C++ wrong. And so if you make a mistake, then bad things happen. And when you have a web browser that's deployed to hundreds of millions of people, you have not only like a responsibility as a product, but you almost have this ethical responsibility to make sure that your code is like actually safe for people. Like web browsers are the kind of things that like nation states want to attack, and you want to make sure that people are safe and protected on the web. And so the idea was, what if we could make a language that would be able to be as efficient as C or C++, but not actually as dangerous? I have a couple more slides on this topic. Basically, Rust is for when you gotta go fast. This is Sonic the Hedgehog, drawn very poorly. So, like, traditionally, when you think about programming languages, there's sort of this axis that people talk about. And so there's sort of like speed on one side, and then safety on the other. And by safety, we basically mean the like what I was talking about before. If you use a pointer and you use it wrong, then your entire world comes crashing down. Hackers steal all your Bitcoin, send emails that are fake, like all that kind of bad, terrible stuff. And so a lot of programming languages used to be incredibly on the speed side and did not care at all about the safety. And that's because computers were significantly worse than they are now. We needed the speed because computers were slow. And so like the only thing that you could do was try to eke every single bit of power out of your hardware. If you've ever looked into like how Nintendo games are made, for example, the amount of tricks and like stuff that they do is really amazing. And if you look at like original games versus the games that came out at the end of the console's life cycle, you'll see that as they learned more and more tricks, they were able to get more and more power, and the games look better. And this has been true with like hardware in general. There's a very famous Usenet thread. Does anyone remember Usenet? Cool, some people do. Usenet was like Twitter, but over email, which is a terrible, terrible description. But there was an old thread long ago between Linus Torvalds and Andy Tannenbaum, a very famous operating system professor, and they were arguing about like the Linux kernel and its architectures or whatever. This is like a famous flame war, like back in the day. And as one part of it, there was a description of like, pretty soon we're gonna have computers that can do like 400,000 operations per second or something like this. And so I looked up like what my iPhone was at the time. I did this a couple years ago, so it was like an iPhone 6 or 7, and it was like, the iPhone had like 7 or 8 orders of magnitude more speed than the computers that they were talking about back then. And I was like, this thing I'm looking this up on is like far more powerful. And so as we've gained like not as much need for speed, people have focused more on safety. So 1995 was like an amazing year for programming languages. Java and JavaScript and I believe Python and Ruby, like almost, Python was a little earlier, it was Ruby, all came out in 1995. I don't know what they're putting in the drinking water, but it was like an amazing time for programming language design. And one of the things that came out of this sort of like era, and this is even true of C at the time, is like assembly is too dangerous, so let's build this programming language called C because it's like higher level and easier to use and you'll make less mistakes. And so we've been like trying to add safety on top through programming language design to make it easier for you to write programs that are correct and harder to write programs that are incorrect. And so a lot of this early focus and the research that happened on garbage collection, for example, garbage collection handles a lot of these sort of areas around memory where you no longer have control over how memory is allocated or deallocated. The language does it for you via the runtime, and so you don't have to think about it. And the problem there is that it's much slower than a language that is not. So we have this trade-off between speed and safety, and I like to pick on Ruby because I worked on Ruby for years. I love Ruby. I have a Ruby tattoo, so I'm going to use Ruby as my stand-in slow garbage collected language in this talk. But like, we sort of had this dichotomy where it's like, yeah, you can either use a language that's nice to use and easy, but also extremely inefficient, or you can use something that's very, very fast and very, very dangerous. And so like, Rust came along and said, why can't we actually have both? And the answer is because everything is always a trade-off. So Rust is like, haha, we have speed and safety. But the thing is that you're always paying somehow. And so the answer in Rust case is it's more difficult to learn. And there's a lot of like slower compilation. You get a lot of compiler errors because the compiler is very strict. And so it takes a little more time to get going with Rust than it does with something like JavaScript. So there's always a trade-off somewhere. Whenever somebody has a slide and they're like, look at these two bad things, but I have something that's better than both of them. Like, if they don't tell you why that's also bad, they're just lying to you, probably by omission. And so this is actually like a really significant problem across a lot of software, this idea of safety. And people keep reaching, because there are applications that still do need speed, people keep reaching for languages that are memory unsafe. So this is a chart put out by Microsoft, and it shows security vulnerabilities across all Microsoft products. So this is not about a particular language. This is everything Microsoft has ever done. And you can see it goes from 2006 to 2018, and it shows what percentage of security vulnerabilities in Microsoft products happen due to memory unsafety issues. And the dark blue is memory safety issues, and the blue is all other issues combined. And what's interesting and weird about this is that it's basically been at 70% across this decade plus of time, roughly. Obviously a little more sometimes, and a little less sometimes, but basically about 70%. And so the idea of Rust is like, what if you could just eliminate roughly 70% of your security vulnerabilities like straight off the top? And it's important to note like that a lot of people saw this chart and thought that this was like against C or C++, but that's also not necessarily strictly speaking true. Like in a dynamic language like Ruby or JavaScript or Python, we often reach out to lower level languages for speed. Like Node is written in C++, and so if you're calling into Node's native APIs, just because you're using a language that's garbage collected doesn't mean that the language itself is implemented in something that is. And so you can have these kinds of issues even in languages that are normally safe because of the implementation. And so this is kind of like the idea. There's a really great series of webcomics that showed programming languages represented by various kinds of people. And this is the one that they did for Rust. It says, I'll be your designated driver tonight. And the speech bubble says, we know. And the second one says, don't talk while eating because you could choke and die. Ha ha ha. And so she's got this like really strong armor because this is like a thing that we particularly care about. And so I always find this really funny. I have links at the end. I'm going to make a lot of references to this talks, and rather than put them on the individual slides, I shove them all at the end. So I have a link to the comic and all the other stuff I'm referencing. I have links at the end. But if you check it out, it's really, really funny. She did like 10 or 15 languages, I think. Okay, so I mentioned this stuff about garbage collectors and like Node and stuff, but like let's get a little bit more into what exactly that means. So there's this concept called a runtime, and it's one of the most overloaded words in computer science and in programming languages because they mean a ton of different things. Lots of people say that languages like C and C++ have no runtime, and languages like Ruby, JavaScript, and Python have a runtime, but that's actually not strictly speaking true. Assembly is the only language that doesn't have a runtime. C and C++ and Rust like have a small runtime. So I have like the light gray is like your code, and the dark gray is the runtime code. And what this means is the stuff that your programming language puts into your programs that you didn't actually write. And so like with JavaScript, you get all of V8. Like if you build a Node program, like you have V8 and all the rest of Node, and that takes up a significant amount of the total space of your program outside of just the code that you actually like wrote. And so we tend to say that those are like big runtime or like has a runtime languages, and stuff like assembly and Rust have like no runtime, even though it's like technically not true. It's like almost true for languages like Rust. And so this is interesting for a number of different reasons, but I'm not going to really super explain why right this second. I'll get there. I mentioned compiler errors. Because Rust really wants to be helpful, and like the first part of the slogan was empowering everyone, right? So we wanted to make sure that we had the ability to help people write good software. So we invested a lot of time into good error messages. So here's an example, some Rust code where we declare a variable y, but we never give it a value. And then we try to pass a mutable reference to it to this function add1, which takes a reference to a 32-bit integer and adds 1 to the number. This is a problem because we never gave an initial value for y, and so this number could be anything. It's just garbage memory. And if you wrote this, C programs that write the similar thing would compile. I believe recent compilers have some diagnostics for simple cases like this, but Rust will always check. And so here's an example of an error. It says, hey, you have a possibly uninitialized variable y, and you used it when you passed it to add1, so you can't do that. Please don't. And so there's sort of a running joke that's like, what's the answer to every single Rust programming question? And the answer is compiler error. Like, because it really like enforces this kind of discipline on you. But eventually, you sort of, once you get like a feel for it, it almost feels like a pair programmer. It's double checking your work behind your back, and that means that you can be really confident that even when you're writing really low-level code that needs to go very fast, Rust has your back. And that means that you can do really, really awesome and complicated things. And that's a really important part of Rust. And it's why we've seen a lot of people, like I came from the Ruby world. We have a lot of JavaScript people in Rust now. And they would have never used C or C++ because they know that they don't know a lot about these things and that the consequences are dire. And so like ironically, by making the language a little harder to use, we help people learn these kinds of things and write software that's reliable, even if they don't have like low-level programming experience. And so we're sort of expanding the audience for people that are able to write, anything down the stack. Like you can write an operating system in Rust, and there are several people who have done so, and that's really cool. All right, enough about Rust for now. Let's move on to part 2, which is WebAssembly. As the web has like grown, like originally, the web just had these very basic static documents, but we weren't really happy with just having some text on a page. And so CSS came along and allowed us to style our web pages. And then JavaScript comes along and allows us to add code to those web pages. And so even in the earliest days of the web, we were more ambitious than just purely documents. It's only been more recently that we've been trying to be truly ambitious, but like, going from plain text to like some amount of fanciness was definitely an aspect of this. And it's because like the web is a platform that connects everybody in the world, as I believe Sarah said at the end of her talk yesterday. And so, we want to be able to connect with other people and share experiences and build more cool and interesting things. And so in order to do that, we need to be ambitious with what the web platform actually allows us to do. And over the last decade, or maybe even 15 years at this point, God, I feel old. We've been like significantly expanding what the web can actually do as a platform, and that's because we all love the web and we're trying to push it forward. That's like kind of, in some degrees, like a large part of this conference, right? And we've seen a lot of great talks over this conference about different ways in which people are trying to push the web to its limits and make it do things that it's never been able to do before. And so we've sort of like leaned into this idea that like the web should be everything to all people. It's kind of ironic, actually, that the Apple iPhone store exists, because originally, when it came out, there was no way to make apps for the iPhone. And Steve Jobs' answer was, you should make web apps instead. And we weren't ambitious enough, and people were not able to make web apps. And so then they caved in and said, fine, we'll make an app store and give you a way to write Mac apps. And now that's like the great battle of like native versus the web. But like we actually were winning at the start, which is the thing that a lot of people like forget. That like the App Store wasn't like created by Apple to destroy the web. Like Apple tried to tell us to use the web, and we just didn't. So they said, okay. And so we've been like ever so slowly like building up these capabilities. And it's fantastic that you can do like animations and VR and like Web USB is like a spec that I'm always like a big fan of, just conceptually, like access your USB drive from a website. Like that like sounds really cool and like lets you do all sorts of things that you would not be able to do before. But yeah, we have to be ambitious. And so a long time ago, there was this project that came out of Mozilla called ASM.js, and it was one of the first attempts to make the web more ambitious in a specific sort of way. This is described as an extraordinarily optimizable, low-level subset of JavaScript. And basically, what happened was the folks at Mozilla had seen that people were doing like compile to JavaScript languages, and there were a ton of them, and there still are a ton of them. And so they realized that like JavaScript had often become this like compile target. I mean, even if you write plain JavaScript today, if you have Babel and Webpack installed, like it's going to compile your JavaScript into other JavaScript. And so like even people that write regular JavaScript today are often compiling it into other JavaScript for backwards compatibility reasons. And so the idea was, what if we could take what we know about how browsers optimize JavaScript and then figure out what parts are easily optimizable, and then give people the ability to compile their code into that optimizable form, we could make really amazing things. And since it's still a subset of JavaScript, it's just JavaScript, it would still work even if it was not highly optimized, it just might be slower. And so this is a really interesting idea because like a lot of times when you try to expand things, you only let the people who like are able to use the new things use it, and it's hard to gain traction. And the idea here was to sort of, you know, instead of like making a whole new way of writing web apps on the web, like putting a new language in the browser, for example, why not just keep using JavaScript? Why put a new language in the browser when you could compile that language to JavaScript if we could make that process more efficient? And so this is sort of what ASM.js tried to and largely succeeded at doing. Here's an example of some ASM.js JavaScript code. So this is a function called compiled calculation. It calls out to two functions, f and g, and it ORs them with 0. This is a bitwise OR. I don't know if you've ever seen or used this in JavaScript before. And then it returns those two numbers also ORed with 0. And the comments here is like x is a 32-bit value, and so is y, and this will do a 32-bit addition. If you know anything about bitwise OR, which I would forgive you if you don't because it's really boring, basically this doesn't do anything. You're saying like, you know, OR every single one with 0, and so 1 OR 0 is 1, and 0 OR 0 is 0, so the numbers stay the same. So this looks to a human like a no-op. But it's not actually a no-op because of the specification. You can really get deep into the weeds with specs, and a lot of people like to, including myself, including people who design programming languages. And it turns out that this actually is guaranteed to be a 32-bit integer, not actually a floating point number, even though JavaScript does not have floating point numbers. So you would maybe write this code like this, but this code, which is semantically equivalent to the previous code, is actually like slower. And by now, you know, JavaScript engines have gotten fast enough that sometimes they'll do this on their own, but like basically integers are faster than floats. The only type of numbers in JavaScript are floats, so this naively would use a float, and so it would be slower. The reason why is in the spec. So this is a link, well, not a link, but like the part of the spec that makes this happen from the ECMAScript standard. And it says that all of the Boolean operators where like A at B, where E is one of the bitwise operators, so like the OR that we saw before, it does this. And so it first gives you the result of evaluating the thing on the left, and then it evaluates the thing on the right, and then it converts them into 32-bit integers, and then results in a 32-bit integer. So like inside the JavaScript virtual machine, even though you can't use integers in JavaScript, JavaScript has integers. And so this is like a weird hack that lets you sort of like abuse this semantics to get integers in JavaScript, even though, I mean, big int is coming, but it's not here yet, and big int is different than this. to get integers in a language that doesn't have any, which is like kind of wild when you think about it. And it's not super surprising that there's some of the folks who are on TC39 that came up with this idea of ASM.js, because they're the people that know this kind of stuff. Like, I didn't know this at all. But you're sort of like, it's not like abusing the spec exactly because it's following what the spec says, but it's just like in an unusual way you wouldn't determine like on your own. And you don't have to think about this because that's the whole point of this compilation process. The idea is that you write the code that looks like this, and then maybe it would compile it into something that looks like this. And so that would like let you be able to do these kind of things. So this resulted in this demo. I don't know if anyone remembers this. This screenshot is a little blurry. I'm sorry about that, which is like unfortunate given that it's like a graphics demonstration, but also this is like a long time ago, and so these graphics are not as impressive anymore. But like I remember loading this page up in my web browser, and this is the Unreal Engine. It's a couple million lines of C++ code, and at the time, this is like hyper cutting edge graphics. And I could like walk around in this medieval town in my web browser. And I was like, holy crap, like this is amazing. And it took like, I think it was around a week of folks from Unreal and Mozilla compiling the Unreal Engine to ASM.js and being able to run it in Firefox. And you would get this kind of like rich 3D, and it performed like surprisingly well. And this is like really cool. And this is where I first personally like became convinced that making the web ambitious was like really important and a good idea, because like I was like, wow, once you could do like 3D games on the web, like the web can do anything. Like 3D games are one of the most CPU intensive things that you can possibly do, at least in my opinion at the time. And so I thought this was like extremely, extremely impressive. But ASM.js was not the end of the story, which is why this talk is not about ASM.js. It turns out that while ASM.js worked, it also sort of didn't. And what I mean by didn't is that we could actually do better. The fact that ASM.js was JavaScript was really good for compatibility reasons, but it also had some limitations. It's still JavaScript, so it still requires the interpreter to like parse all of the JavaScript code. It's a little more verbose. If you notice, we added those or zeros, so actually it could sometimes be larger. And like we're all trying to reduce our bundle sizes, right? So like the idea that you make something bigger is like also a problem. And like all that time was like of compiling the code and like doing all this stuff was strictly speaking unnecessary, and it was limiting the speed that ASM.js could do. While it was faster, we could get even faster. So enter WebAssembly. After ASM.js proved that doing this kind of thing was possible on the web, in like a miracle of standards that never actually happens ever, everyone got together and like agreed on something. And so we ended up with WebAssembly. And WebAssembly is this kind of like spiritual successor to ASM.js, but it's sort of like, what if it wasn't a terrible hack, but it was like something we all planned out together and like made sure that it was good from the start. And so to give you an idea of like why, this is an ASM.js version of the Fibonacci function. You also notice this interesting string use ASM at the top. This is another interesting failure / success of ASM.js, in that originally the folks thought that browsers would read this string and go like, oh, this is ASM.js, and turn into a super faster compiler instead of the regular JavaScript compiler. But the folks at Chrome were like, why don't we just make JavaScript faster in general and we'll just ignore it? And so they actually never implemented ASM.js specific optimizations. They just made JavaScript faster and then it worked. So, oh well. But anyway, so like, so you can see all these or zeros here in this Fibonacci function, and you can see that at the top is 185 bytes in size. That's how big this code would be if you send it over the wire. Not that big. But if you look at the WebAssembly code down here at the bottom, and yes, it's almost all boxes because it's not actually, like it's binary code, like ASM.js is binary, so, WebAssembly is binary, so like it doesn't really render here. But the point is the equivalent Fibonacci function written in WebAssembly ends up being 62 bytes. And so this is much smaller and more compact, which means that you're not sending as much data over the wire, which means your pages load faster. It also is significantly easier to parse because of the fact that it's binary, and so it's much faster than parsing a real programming language like JavaScript, and so that also like significantly adds on to these kinds of like speeds. So it's smaller and faster, and you know, you don't write this by hand. We'll get into there in a minute, but This is an image from Lynn Clark, who gave a great talk yesterday. She does these code cartoons that are awesome, and so I wanted to use one of them. The idea is you don't write WebAssembly by hand, although you can. There is the WebAssembly text format, or WAT, and you instead would mostly write other languages and then compile them into some, in this case, like LLVM-IR in this example, but like the point is you compile them to WebAssembly instead of writing the WebAssembly format yourself. And so the idea was that you no longer needed to like only write JavaScript, you can write other languages as well, and they would be able to like work inside of your browser. And that's like really, really cool. The WASM like 1.0 release, like the MVP, shipped a little while ago actually. And so if you look on Can I Use, it's 87.42% of browsers today support WebAssembly natively. So if you need to use old IE, not Edge, that's actually the biggest holdout. So like you can, as long as you don't need old IE, then you can use WASM basically. I guess if you care about Opera Mini, maybe that also matters to you too. But like basically all modern browsers all have good WebAssembly support at the moment, and so it's like surprisingly accessible, even though you may not have realized that it's actually started shipping. So that's really cool. There was a joke made by our great MC yesterday, but well, this is sort of related, but not entirely the same thing. But like one funny thing that like WASM people say all the time is WebAssembly is like a funny name because it's neither web nor assembly, actually. It's not an assembly language, it's a binary format. And while it was born out of the web, it's actually significantly broader than the web is. It was designed in a way that like the spec says nothing about the web or web browsers. It describes how WebAssembly code interacts with a host environment. And so the normal host environments are browsers, but you can write other host environments to be able to put it in whatever you want. So this is a talk that's amazing. It's called The Birth and Death of JavaScript by Gary Bernhardt. Has anyone seen this talk? Cool. I was lucky enough to see this talk live, and it like blew my mind. It happened when ASM.js existed and before WebAssembly existed, so it's a little different now. But it's a fake talk set in like the year 2050, talking about the history of JavaScript since the early 2000s till now. And so he talks about how once you can compile programs into what he called Metal, which is basically what WebAssembly is, you would be able to say like if you can compile a program, then you can compile like anything, because compilers are great. So what if we would compile our browser to WebAssembly? And so this is a screenshot of GIMP running inside of Chrome, running inside of Firefox, is the idea. And like, you may think this is ridiculous, and it is kind of ridiculous, and I laughed when I saw it, but I've been telling Gary that like over the last couple of years that like his like sort of nightmare has been my dream, and I've been trying to make this actually happen. And I didn't end up making this happen, but my ex-colleague Dan Callahad managed to compile DOSBox to WASM and then load up Netscape Navigator inside of DOSBox inside of Firefox. So like if you thought that previous slide was ridiculous, like this is actually like a year old, like it's already happened. Like we're past that point now. Maybe you'd want to browse the web as something better than original Netscape Navigator, possibly. So it's not like we have Chrome inside of Firefox yet, but like the point is that like conceptually this works. Obviously there's some fine details to work out here, but like it is a thing that is real and has occurred already in the world. All right, so pick it up a little bit. Rust and WebAssembly. This is part 2.1. So I talked a little about Rust and talked a little about WASM. So we showed this code earlier with the like ASM.js and the WebAssembly, but one of the reasons why this ASM.js is so small is because it basically only uses like language primitives and doesn't really use anything from the language itself. This is an example of assembly script, which is a subset of TypeScript that compiles to WebAssembly, and it's a more complicated example. This involves giving you 64-bit integers in JavaScript by writing a library that implements them in TypeScript or whatever. And so it's 6 kilobytes of source code in TypeScript. But like, as we talked about before with runtimes, like WebAssembly doesn't give you a runtime. So if you use a language that has a runtime, you have to bring it along with you. So like languages like Rust having a small runtime means that their WebAssembly code is very small. But languages with a larger runtime, like TypeScript, although the assembly script runtime is relatively small, but language like Python or Ruby or Go, you have to bring the entire runtime along with you. And so it creates bundles that are much larger, and it's harder to make them smaller due to the runtime being necessary for the language to actually work. And so in this example, the assembly script generated code is actually much larger because you have to include the assembly script runtime. And I should mention they actually give you options for different runtimes, and so you can do like a always leak memory and don't include a GC runtime, which is useful for some things, but like reduces the size. And they put a lot of work into making it more usable. So it adds about 2 kilobytes onto your binary, which is definitely not bad, but it's always an extra 2K. So we saw this opportunity with Rust and WebAssembly becoming a bigger thing, and a year and a half ago, in 2018, we decided to start a WebAssembly working group, and they've been producing amazing tooling around Rust. There's the WASM BindGen project that was implemented by them, the WASM Pack project that's been implemented by the working group, and a bunch of other really interesting tools around WebAssembly because we really believed that like WebAssembly is a cool part of the future, and we want Rust to be a part of it. And so it's generally considered that Rust has the best-in-class tooling for building WebAssembly stuff, and so they've been working together like for a while on these things. Part 3, serverless. I haven't really mentioned anything about like servers or stuff. This is the joke that was made by our MC yesterday and pointed out very aptly, like the problem when you talk about serverless is everybody's like, there's still servers in serverless, ha ha ha. Like, yeah, okay, we get it. Like it's not funny or insightful actually. I'm not going to explain to you why serverless is important or why it's cool, because I already had so many things in this talk that I could not fit it into the time. I'm assuming that the people at this conference already know stuff about serverless, and so I'm not going to explain like all the details here. There's a bunch of other talks about that, including at this conference. But I do want to talk a little bit about some parts of serverless. This is one of many charts you can find online about a history of the cloud. And how we went from like the data center and VPSs to infrastructure as a service, and then platform as a service, and now serverless. We talk about this progression. But the interesting thing, I think, is that most people forget or didn't notice that there's actually a really subtle shift that's going on here. And it happens in between this infrastructure as a service and platform as a service idea. And that's because of this question: what API does your hosting platform offer? And I think when most people think of APIs, they think of like some sort of webhook thing. But I mean like a platform that gives you the ability to host your code needs you to have some sort of interface that your code runs against. And so like in the data center and in IaaS, Unix was the API often. There's Windows and stuff too. Like Unix was the API they offered you, which means you could do whatever you wanted because most programs like ran on Unix. But that was basically the interface between you and the cloud provider. They would say, I'm going to give you a piece of hardware or virtual hardware, and it's got an operating system on it, and you can SSH in and like do whatever you want. Like you can interact with it in that way. And a lot of people don't think about Unix as being the API, but it was. And this is the shift because between IaaS and we went to platforms as a service, it now meant that your application and what you wrote it in became the API between you and the hosting provider. It took me a little while to dig up this next slide, but oh yes. This is Heroku's like original web page. This is in October of 2008. You notice the good beta tag up there on the left? Like this is like prime like Web 2.0 like awesomeness of web design. But it's a Ruby on Rails platform. Originally with Heroku, like you couldn't run whatever stuff you wanted. You could only run Rails applications. And that's because the idea with the platform as a service is that you would just upload your app and you would never SSH into a server anywhere, and they would figure out all the details. And that meant that the server provider had to provide an API, if you will, for every single kind of application that you wanted to run. And that meant that that was like more difficult because they couldn't just support Rails only, and as they grew, they added other languages and did other things, and so did all the other providers. But I think this shift between giving a general OS and giving an application-specific thing is like more significant than we think. Yeah, it was the Rails platform. There was this company called .cloud that existed around this time. This logo is also fuzzy because almost all their stuff has been like scraped from the web at this point. They were a similar Heroku-ish provider, but they were one of the first that I personally remember that offered the ability for you to use more than just one particular kind of thing. And that's because they were working on this technology that you may have heard of called Docker. They ended up open sourcing Docker, and then their business imploded because it was open source, I guess. I'm not totally sure if that's true, but like .cloud morphed into Docker, and that's why I couldn't find their logo. It had to dig really hard because it was like difficult because their website's gone, and archive.org doesn't have it either, which is strange. But anyway, Docker gave these platforms the ability to, again, offer an operating system as the like unit that you would be able to give to the platform as its API, so that you'd now be able to support all kinds of other things. And that's when we get tools like Kubernetes and all these other sort of aspects. And so instead of us having the platform-specific APIs for each particular language or runtime, we instead had Docker, and you would just run a bunch of containers everywhere instead of SSHing with server or like uploading your application-specific thing. The platform would essentially implement Docker containers, and you would hand them a container with whatever you wanted in it, and then you could do anything. And this made things much easier. All right, I'm almost done. I have one little last bit here, and that's about the future of serverless. I'm going to blow through it because I know that you all have lunch next, so I don't want to hold you too hard. So Docker is a container, but you know what else is like a form of container? A web browser. It turns out that you download and run arbitrary code from arbitrary sources every single day. I'm doing it right now in Google Docs to make this presentation. And so like, it turns out that if you squint hard enough, these are almost the same thing. Like, we had this particular diagram before. This is the same diagram as that Docker diagram earlier, where you make a Docker container and you upload it to the servers. You can write WebAssembly, and like, it's almost the same thing as Docker, which gets us back to that original tweet. If we'd had a runtime that was isolated, then these hosting providers could have offered an abstracted way to run whatever code you wanted without like needing to do all this isolation stuff themselves. And so this also referenced the original tweet as WASI, which is this sort of extension to WASM. And if you want to learn more about WASI, I suggest that you get in your nearest local time machine and go back to yesterday and watch Lynn's talk on WASI. Sadly, she's not after me, so I can't tell you to go to it. But if you saw it, she went into the details of what WASI is and all these things. But I'm not going to get into that super deep. I'm just going to say that WASI lets you sort of like break out of the sandbox in a controlled way. So it gives you access to things like the file system, but also lets you control what kinds of things the application is allowed to do. And so this combines with the last topic I want to talk about today, which is edge computing. I work at Cloudflare, but this is not a Cloudflare product pitch. This is also a thing that Fastly is doing. So, but this is like a trend that's been happening lately that I don't think a lot of people are also appreciating in the serverless world. Here's a list of AWS locations. There are 69 of them, according to AWS's website, and they're planning on some more. So if you are a user, say you're in West Africa, and you want to use something that's on AWS, then you've got a long way to go to get to wherever your code is actually hosted. But if you look at the network of people like Fastly or like Cloudflare, there's significantly more locations around the world. And that's because they were trying to build a global network for CDN and security purposes, and they weren't trying to build a bunch of server farms. But like, both of these are basically giant buildings with a bunch of computers in them. So at some point, Cloudflare and Fastly both kind of realized, hey, we sort of have a bunch of server farms, and we have a lot more of them than AWS does. And so there was this old slogan in Java times called write once, run anywhere, and that meant that your code was platform agnostic, and so you could run it on any part that you wanted. But this is like write once, run anywhere, like in a physical sense. Like, you write your code one time, and then you deploy it to all of these things simultaneously. So in the AWS model, it gets deployed to the particular locations that you want to and pay for. But in this world, you just write your code once, and it goes to the edge of every single node in both of these companies' networks. And you can also sort of do this with Lambda at edge, which runs a subset of Lambda on CloudFront. So AWS is also doing this too. I just don't think they're pushing this as hard. But what's enabled this to happen with these smaller companies, like Cloudflare and Fastly are not the size of AWS at all, is due to WebAssembly. And so instead of having to build out all the separate runtimes for these different features, they're letting you run WebAssembly code on the edge. And so Fastly's thing is called Terrarium, and ours is called Cloudflare Workers. And effectively, you're able to like write your code in whatever you want, compile it to WASM, and then run it everywhere all over the world. But to tie these all things together, what's interesting about this is that because of all that work that we've been putting in with Rust to make WebAssembly tooling awesome, the runtime that they use at Fastly, called Lucet, and a lot of our tooling, Wrangler is the command line app that lets you build stuff for Cloudflare's products, these are all written in Rust. And we're seeing an increasing amount of stuff around the WebAssembly space be implemented in Rust, because Rust already has these tools, so it makes it easier to build stuff, and all that stuff is there. So that's That's why the Rust tie-ins. This is kind of like how all these random things are sort of coming together. These are the takeaways from my talk, if you will. The first one is that Rust loves WebAssembly and vice versa. WASM and serverless are thinking about it. I'm not sure this is a thing that's actually going to happen, but we're trying to make it happen. This is one possible future. I'd be lying if I could tell you that I knew the future for sure, but this is an interesting thing that I'm seeing happen and I think is going to be more significant. And then finally, edge compute is like a cool idea and you should check it out. And I think that it's a really interesting extension of the serverless model that we've all been using for the last couple of years. Thank you so much, and please enjoy lunch.